welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson 3, Exponential Growth and Decay. Before we begin, let me remind you that a worksheet and a homework assignment that go along with this video can be found by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes at the top of each one of our sheets. You can use your smartphone or your tablet to scan that code and bring you right to the video that goes along with this lesson, which of course you're watching right now. Anyhow, let's get started. In the last few lessons, we reviewed exponent properties, and we extended our understanding of exponents to to zero exponents and negative exponents. All of that is going to be necessary for what we do today. You see, today we're going to start to model phenomena that grow or decline/decay exponentially. Now, the idea of exponential growth or decay is the idea that the rate at which the quantity is changing depends on how much of it there is, right? So the more of it is, the faster it grows or declines. The less there is, the slower it grows or declines. And one of the greatest examples of that is how a rumor spreads. So let's take a look at exercise 1. The number of people who have heard a rumor often grows exponentially. In other words, it grows faster the more people that know it. Consider a rumor that starts with 3 people, where the number of people who have heard it doubles each day that it spreads. Okay? Now, letter A. Let's just make sure we understand why we would model this with an exponential function as opposed to, let's say, something like a linear function. Why does it make sense that the number of people who have heard the rumor would grow exponentially? Pause the video now and think about this and then try to write something down. All right, well, it makes sense to me because the more people who know the rumor, and I'm not saying spreading rumors is a great idea, we're just modeling it. The more people who know the rumor, the more people who can spread it or tell it to others. Now, there's a certain extent to which that wouldn't be true. You know, if you were in a small closed population, the rumor might start to grow, or the number of people who knew the rumor might grow very quickly at first, but eventually it would slow down because, you'd go up to somebody, tell them the rumor, and they'd be like, yeah, I already heard it from like 5 people. But if we're talking about kind of an unrestricted population, then the more people who know the rumor, the more people who can tell the rumor. All right? So in letter B, it says, fill in the table below for the number of people, n, who knew the rumor after it has spread a certain number of days, d. So in other words, right, the rumor starts on day 0, if you will, with 3 people knowing it. The next day, day 1, 6 people know it. The next day, day 2, 12 people know it, right? Because what we're going to be doing in each case is we're going to be multiplying by 2 to get to the next quantity. All right, day 3, 24 people would know it. Day 4, 48 people would know it. Day 5, 96 people would know it, right? So, simple enough, all right? But what we're going to do for the rest of the problem is now try to model this mathematically with a function, specifically a function in equation form, all right? So I'm going to clear out the text. You write down what you need to. All right, let's do it. So continuing with the same problem, anytime I continue with the same problem, I'm going to just keep having the problem's description up above. Now, here in exercise 2, right, what we want to do is we want to determine the number of people who know the rumor after 20 days, but to do that, we're going to develop a formula to predict the number who know it. We'll call that big N, if we know D, the number of days it's been spreading. So this is kind of cool. What I'd like to do in letter A is really understand how to develop this formula. And to do that, we have to dig into the math that's used. Right? We know that we're going to keep multiplying by 2, But what does that really mean? Right, on day 0, we simply have 3. On day 1, right, we have 3 times 2, which granted gives us 6. Day 2, though, we take that 6, right, and we multiply it by 2. But that's really based on the associative property of multiplication, the same as doing 3 times 2 squared, right? And then day 3, we've really got that 12 times 2, but that was 3 times 2 times 2, right? That was my 12 times another 2. So that's going to be 3 times 2 cubed, or 24, right? Day 4, you probably see what's going on. That's going to be that 24 times 2, but that 24 was 3 times 2 times 2 times 2, then times 2 again. So 3 times 2 to the 4th, or 48. Day 5, well, that's going to be that 48 times 2. I know this gets to be a little bit much, right? It's going to be that. There's my 48 times 2, which is going to be 3 times 2 to the 5th, which is going to be that 96. So look at what we're really doing. What we're really doing is counting how many times we double, right? And that just depends on how many days have gone by. And then we're multiplying by 3 the number of times we double, okay? So B says, using the pattern you developed in A, write a formula giving the number of people who know the rumor, N, if you know the number of days, D, it has been spreading. All right, well, again, watch me track it. I'm going to actually circle the number of days. Actually, let me put here, just so that we really see the pattern. Right? Look at that. Day 2, there it is. Day 3, there it is. Day 4, there it is. Day 5, there it is. So what's my formula? My formula is that the number of people who know it will always be 3 times 2 raised to the number of D. Right? This just tells me how many times it's doubled, or how many double. I'll call it how many doubles. I'm not sure if that's the best way to put it, but that's how many doubles, and then 3 is what we start with. So if we want to know how many people, let me use function notation, know the rumor after 20 days, we just need to multiply 3. Actually, let me get rid of that for a second. We just need to multiply 3 by 2 to the 20th. Now this is certainly something you're going to use your calculator on. But if you type it in as 3 times 2 raised to the 20th, what we'll find, is a lot. 3,145,728. Now you might not think that's very reasonable, right? Wow, 3 million people knowing a rumor. But think about how quickly things can spread through Facebook or Twitter or what have you, right? You know, that could easily double every day. And where you start off with 3 people knowing a rumor, 20 days later, 3 million people. Wow, over 3 million people know it. Now, letter D says exponential growth can be very fast, as we saw. Assuming our equation from B holds, how many days will it take for the number of people knowing the rumor to surpass the population of the United States, which is approximately 315 million people? Show calculations that support your answer. So what I'd like you to do is play around with your calculator, right? Just play around with it. We know we're not hitting it at 20 days, right? At 20 days, about 3 million. No, I need to get up to 315 million. So play around with your calculator and see what you come up with. All right, well, here's what I found. In Algebra 2, you're going to find algebraic ways of doing this, but right now we just kind of do it by guess and check. If I evaluate the number of people after 25 days who know the rumor, 3 times 2 to the 25th, and again, in your calculator, you can put that in a variety of ways. This actually works well if you use this, right, with the caret, we find that that is 100,663,296, which is too small, right? We're looking for 315 million as of the time of making this video. But we're getting close, that's 100 million. So after 26 days, 3 times 2 to the 26th, we end up getting 201,326,000. Sorry, I can't do this in my head. 592, still too small. But after 27 days, we're going to pop above the population of the US. That would be 402,653,184. So there it is. That thing's more than it. So we would say 27 days. Amazing. Now, again, you can make a fair argument. In fact, I hope you do make a fair argument that that is just completely unrealistic. Completely unrealistic that a rumor would spread so that the entire population of the United States knows it in less than a month. Less than a month. But again, although that may be unrealistic, it's probably not unrealistic that rumors do spread quickly and spread exponentially. In other words, the more people that know the rumor, the faster it spreads. All right, I'm going to clear this text out, and then we're going to take a look at a kind of a funny example on decay. Okay? All right, here it goes. I'm going to clear it out. So, Helmut. That's a real name. Not kidding. It's a Finnish name. Helmut is heading towards a lighthouse in a very peculiar way. By the way, I'd suggest trying this sometime. Maybe not with a lighthouse, but with something. He starts 160 feet from the lighthouse. On his first trip, he walks half the distance to the lighthouse, right? So, here's our friend Helmut. Probably insulting Finnish people right now. And he walks halfway, right? And on his next trip, he walks half of what's left. And on his next trip, he walks half of what's left, etc. All right? What we're going to model is how much distance he has left, how much distance is remaining to the lighthouse after n trips. Okay? Now this is what's known as a decay problem, or an exponentially decreasing function, because obviously the amount of distance he has left is going down. It's decreasing. Okay? So let's take a look at letter A. Fill in the table below for the amount of distance that Helmut has left after n trips. Well, after 0 trips, after he hasn't gone anywhere, he still has 160 feet left. After 1 trip, though, right, he's sitting here, and he has only 80 feet left. After 2 trips, he has only 40 feet left. After 3 trips, he has only 20 feet left. And after 4 trips, he has only 10. In fact, I almost marked all of those off, right? So that's trip 1, 2, 3, 4. Now, this is very, very important. Exponential functions are all about multiplying. They're not really about dividing. So if I can avoid the idea of division by 2, I'd like to do that. So B says each entry in the table could be found by multiplying the previous by what number? Hopefully by 1/2. Right? Division by 2 is the same as multiplying by 1/2, right? If I took 160 and I multiplied by 1/2, I'd get 80. If I took 80 and I multiplied by 1/2, I'd get 40, etc. Right? And again, we want to be able to think about exponential functions all in terms of multiplication, not in terms of division. Okay? So let's keep going and let's try to extend this, create that exponential function. All right? Pause the video now, write down anything you need to. All right, here we go. I know there wasn't a lot to write down on that page. So we continue to have Helmut. So like in exercise 2a, what we're going to start to do is to develop a pattern, and it's going to be very, very similar, right? After n trips, we've multiplied 160 by 1/2 0 times. After 1 trip, we've multiplied 160 by 1/2 one time. After 2 trips, we took the 80, multiplied by 1/2, but that was 160 times 1/2 times 1/2, which was 160 times 1/2 squared. Now that ended up being 40, but that's not really the point. What I'm looking for is this. Right? After 3 trips, we took that 40 and we multiplied by 1/2 again, but that 40 came from doing 160 times 1/2 twice, and then we multiplied by 1/2 again. So the third trip's distance left can be calculated by 160 times 1/2 to the third. I think you probably have the idea, but that's going to be 20. And the fourth trip would be 20 times 1/2, which is 160 to the 1/2 to the third times 1/2. So 160 times 1/2 to the fourth, which gives me that 10. Now this should be pretty easy, right? This is almost identical to what we did last time. In fact, letter D says, based on C, give a formula that predicts the distance D that helmet has after n trips. Well, here it goes, right? Exponential functions always kind of look like this. What you start with, what you multiply by, and then how many times you multiply. I'll call it how many multiplication. That now looks like how many x's. How many products. All right, but that's it. Look at that. So nice. Let me circle it. Exactly what we had last time. A starting amount. Our starting amount last time was 3. Then our last time we multiplied by 2. Here we're multiplying by 1/2. Now, let's apply it. Let's use this formula. Letter E asks, how far is helmet from the windmill after 6 trips? Provide a calculation that justifies your answer, and don't forget those units. So this is pretty easy. We figured it out all the way up to 4 trips, but now after 6 trips, we're going to get to multiply 160 by 1/2 6 times. Again, in your calculator, you could literally put this in, 160, parentheses around the 1/2, caret for the power symbol to the 6th, and I got to cheat a little bit by looking at this. I almost read off the answer to one of the previous problems, but this ends up being 2.5. And in fact, he's 2.5 feet away from the windmill at that point. 2.5 feet. All right. So I'm going to clear out the screen, pause the video now, and really think about how this formula was developed, because we're going to write a lot of equations of exponential functions soon. And this is a pivotal lesson in understanding how to do that. All right, I'm going to clear out the text. So let's continue on this problem. Letter F says, Helmut believes he will reach the windmill after 10 trips. Is he correct? Well, hey, why not take our function right here and put 10 in? Let's figure out his distance after 10 trips. So we'll have 160 times 1/2 to the 10th. Again, we can put that into our calculator. And we'll get 0.15, it gets a little messy, 625 feet. So I'm going to say no, because the distance doesn't equal 0. Right? I mean, when he's at the windmill, he's going to be 0 feet away. Now he's close. He's 0.15625 feet away after 10 trips, but he's not there. In fact, he'll never get there, and that's the point of letter G. Explain why Helmut will never reach the windmill. Why will he never get there? Pause the video now and see how you can explain this. All right, let's go through it. Well, Helmut will never reach the windmill because there will always be 1/2 the previous distance left. Right? So even when he gets microscopically close to the windmill, he's still going to look and say, well, I have 1 millimeter left, so I'm going to walk half of that. So he walks half of the millimeter, and now he's got a 1/2 millimeter left. So he looks at that and he says, well, I got 1/2 millimeter left. I almost said milliliter. 1/2 millimeter left. Well, I'll walk half of that, which will be 1/4 millimeter, and I'll have 1/4 millimeter left. So he'll always have half of what he previously had left to walk. Right? Letter H is kind of important. It says, why is the domain of this function only the whole numbers? Now remember, domain, because it's been a little while since we've seen this piece of terminology, right? The domain are the inputs, right? The domain are the inputs. So I'm saying that the only inputs that are valid to this function are 0, 1, 2, 3, etc. Now, why is that? Pause the video now and see if you can give an explanation for it. All right, let's do it. Helmet only takes whole trips, right? The model is only valid for non-fractional numbers of trips. That doesn't look like the word trips. Uh-oh, I just got my whiteboard. How do I get out of that? I can't seem to get out of that. Oh. Here, now I'm back. Wow, back and forth, back and forth. Anyhow, so the model is only valid for a non-fractional number of trips. So you might argue, well, he could take half of a trip. Sorry about the mess on the screen. He could take half of a trip, but it's not the scenario that was set up, right? He was taking these whole numbers of trips, so it doesn't make sense to put 1.5 in as an exponent, or 3.5 in, or even a negative number of trips. What would that mean? Even though we can deal with negative exponents at this point. All right? Wow, I got to learn my software a little bit better. Anyhow, pause the video now, see if you can read this, and then we're going to clear out the text and hopefully finish up the lesson. All right, here we go. All right, let's finish up. So today what we did is we did some of the preliminary work on understanding how to model both growth and decay when it comes to exponential phenomena. Now, again, exponential work really falls down on the idea that the more of the quantity that's present, the faster it will grow, or the faster that it will go away. You'll get a lot of exposure with that decay idea when you eventually, and hopefully, take some chemistry and look at what's known as radioactive decay. All right. For now, though, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.